Okay, well, it's a pleasure to have our last talk of the session, and it's Mike who's going to present.
Thank you. All right, so today I'm going to talk about verified compilation of quantum oracles. I'm Mike, I'm at Amazon Web Services now, and this is joint work with these folks on the slide. The first author is Li Li, who's on the job market this year. For anyone who might be hiring in quantum computing, can pay attention. And I should say this is work that I did while at University of Maryland prior to joining Amazon. Okay, so if you've been here for the whole session, you know that quantum computing is neat, and companies and academic research labs and government research labs are investing in it because of the promise of all of the runtime speedups that we could get. So there's computers at IBM, there are computers at Google, there's computers at Amazon and at Microsoft, and there's lots of investment from the DOE, from the NSF, from other US agencies, and of course, government funding agencies across the world. So why are they interested in this? Probably Shor's prime factoring algorithm, I'm sure you've all heard of it, is the thing that got people most excited about quantum computing and wanted to make it become a reality. We can factor prime numbers in polynomial rather than super polynomial time. Unstructured search, Grover's algorithm, you can do what would otherwise be a linear search in sublinear time. Simulating physical systems, just learning about the universe rather than converting them to digital and trying to cram all that data in there. We can do them directly in the quantum computing substrate instead. So as Charles was saying in his talk, the power of quantum computing comes from putting qubits in superposition. So if we have a qubits, 0 and 1, they're written in this ket notation. Those are actually represented mathematically as vectors. So in the left-hand side, you can think of the top element is how much probability, again, using the analogy Charles was using, to apply to the 0 portion, and the bottom number being the amount of probability to the 1 portion. So on the left, a fully 0 number has a 1 on the top and a 0 on the bottom, and a fully 1 number has a 0 on the top and a 1 on the bottom. But in general, these numbers can be any complex numbers as long as they have unit norm, and they can be in superposition when, which is to say both 0 and 1, the cat can be both alive and dead equally. And that state is the plus state. You'll see it once or twice more in the slides. In general, this power means that quantum states are very large. So a n qubit system will require a vector of length 2 to the n in order to represent. And that creates a bunch of problems. Well, it creates the reason for the advantage for quantum computing and problems if we want to simulate quantum computers using classical ones. So operations on qubits are also represented as matrices. That's not so important. Here is the Hadamard operation that takes one of these qubits that's in superposition and produces the qubit 0. And actually, if you apply it, Hadamard is its own inverse. If you apply it to qubit 0, you'll just get that superposition right back. So we can write it this way. Given those sets of operations, as we've seen, quantum programs today tend to be notated as circuits. And those circuits of different operations apply on different qubits, starting from the left. I like the analogy, Mateo's, of musical notation. You start from the left and you work your way over to the right. Quantum algorithms tend to have a common structure. So here on the beginning, we tend to prepare the initial state, oftentimes by putting it in some sort of superposition. You saw that the Hadamard operation there took a 0 to that plus state, the superposition state. So that's often one of the first things that happens. The next thing that happens is some sort of core computation. Sometimes that's an iterated computation. And then finally, at the end, we measure some results. Quantum programming is not easy. The quantum algorithms are tricky. They often involve fancy math. I sometimes think of it as like learning how to solve a Rubik's Cube. You have to you have these 3 dimensions that you use for your qubits, and you have to stash them all in the right places and do things with them so that they all move in lockstep, and this can be tricky to get right. Sometimes it's hard to know that you did the right thing because we don't actually know what the right answer is. If we're doing simulation of physical systems, we're trying to discover new things about the universe, and it may not be entirely clear that the simulation that we set up is actually correct. In general, simulating quantum programs, if I wanted to use it to, say, debug my algorithm, is expensive because of that 2 to the n state problem. If I wanted to set breakpoints in my program, like I do with classical debugging, to do some stuff that Rob was talking about in his keynote yesterday, that's going to be a problem because it turns out every time that I measure the quantum state, again, Charles talked about reversible and irreversible operations. Measurement is an irreversible operation. It will corrupt the state. And therefore, obviously, the moment you take a look inside the box, you've affected what the box's contents are. Those are fundamental problems. Aside from those problems, in the near term, there aren't that many quantum computers. It's kind of like back in the days in the 50s and 60s when getting time on a computer was rare and expensive. It's kind of the same here. Computers are not very reliable now. The abstraction of a quantum bit is noisy and not reliable. And that all of this put together just means that, wow, it's hard to write effective quantum programs today. But of course, as we saw in the last talk and other talks that have happened in the PL community and elsewhere, programming languages and systems techniques can help by building up abstractions and techniques that make mitigating some of these problems possible. So one thing that my group has been working on for the last couple of years is applying formal verification technology to quantum computing. So the idea of formal verification is to take a system that you want to build and to state a formal property about it and to mathematically prove that that property is correct so that the actual code of that system that you ultimately execute has been proved to do what you meant it to do. And maybe the most famous example of a formally verified system is the ComCert verified C compiler that came out of INRIA. It was first the big paper was published in it in POPL 2008, and it's now used in industry by Airbus, for example. It's a pretty exciting achievement that, hey, I can take my compiler, run my C program through it, and I'm sure no bugs. Why quantum computing? Well, if I formally verify my quantum program does what it's supposed to, that addresses the challenges of noise, of intractable simulation and debugging because I've proved that it does the right thing. I don't need to do any of those other things to figure out whether it does the right thing. Obviously, it's not going to help me in the case that I don't know what the right answer is because I can't specify it and then prove it correct. So a couple of years ago, we built a optimizer for quantum programs, kind of in the analog to ComCert, but for quantum. So some of those bugs that Matteo was talking about in the optimizer, no bugs in our system. In fact, we found a bunch of bugs in existing systems by proving these optimizations were correct, and then having a optimizer that's proved correct. You can use it and not fear that your program's result will get corrupted as a result of running it through your compiler. It turned out that the intermediate representation of our system called SQIR also was useful for just stating and proving correctness properties about quantum programs. And so we proved, for example, a full implementation of Shor's algorithm to be correct, as well as Grover's search algorithm. Okay, so what's the catch? The catch is, it turns out that for all of these accomplishments, we only looked at core algorithms and verified those. We didn't look at what are called the oracles, components of those algorithms. So an oracle, this is not the technical definition, but I think it's a convenient one, is basically the classical function that's applied to states in superposition, sort of at the core of that quantum algorithm. So I'm going to prepare my state at the beginning, and then I'm going to run it through some quantum fanciness with all those states in superposition. And the thing that I run it through is often a classical function, so this giant U here. So if we look at Shor's algorithm again, this a to the x mod n, this is a key element of the order finding procedure that makes prime factoring possible. And the way the algorithm works is that it has actually many instances of this order finding thing. That's what the UA business at the bottom is. And then by setting a bunch of control bits in superposition, we essentially try all of the possibilities of finding the order all at the same time. So setting it in superposition, doing all this stuff, a classical function, a to the x mod n, and then doing some post-processing to get the result. For Grover's search algorithm, there's also an oracle, which is, did I find it? I'm going to search through some space, and I'm going to have a predicate function that's going to give me back yes or no is the potential input that I provided, the one I was looking for. And Grover's is going to be able to find that in sublinear time. I have 100 inputs, but I can find the answer faster than in O of 100. And that's going to be this U function once again. That's the predicate function that is iterated through the search. Okay, so maybe the answer is, oh, you should just prove those oracles correct. You did it for those other algorithms. These should be easier, right? They're just the classical functions. But it turns out, again, what Charles said, just because it's easy to say, oh, just run the classical function foo, actually implementing foo as a quantum circuit and making it reversible is not easy. And in fact, on today's hardware, where we have not very many qubits and not very many gates, people want to optimize those oracle functions quite a bit. And every time they do some sort of optimization, they risk that they have made a mistake. So this, somebody asked a question before about the most significant versus least significant bits. So as I'll show you in a second, doing addition using the quantum Fourier transform requires flipping the order of the bits in the middle of the transformation. And in fact, there was a bug in the original paper that forgot to flip some of the bits in one of the inputs. Okay, so all of these little bit manipulations are an opportunity for an optimization and an opportunity for a bug. So we might hope, okay, we'll implement those oracles. At least we could test that they are correct because they're meant to be classical functions. Unfortunately, if you use the most optimized implementation, they aren't actually implemented as classical functions. They leverage quantum behavior. We tried some using simulation on implementations of oracles that use quantum behavior, and unfortunately the simulator just never came back. That's not to say that you couldn't write a specialized simulator, maybe using some of the ideas in this paper, but at the moment, simulation is not going to work in that case. Okay, so our observation is that many of these oracles, because they implement classical functions, they are fundamentally functions from bits to bits. Even though you generate a bunch of bits in superposition, you can reason about the correctness of these functions classically just as a function over their inputs as if they were normal bits. The quantum implementations don't generate new entanglement amongst all of those bits, and it's entanglement that creates the state space explosion that makes things hard to simulate. So we can leverage that observation by making a simpler intermediate representation for quantum oracles, and also it turns out to assist in proving that those oracles are correct, should you want to do that. Okay, so if I start from the stuff that we did before, the SQIR and Vox work, we are now augmenting this work to create a new quantum, high assurance quantum programming stack. And this new part is called VQO, for Verified Quantum Oracles. We first of all design a high-level imperative programming language called OQIMP. That's the one in which you would write your oracle in sort of a C-like programming language. This will compile down to a new intermediate language we call OQASM, for Oracle Quantum Assembly Language. And it's in this language that we would express some of the primitive operators that your high-level language is going to use. Addition or addition modulo a number, or division or multiplication. We'll build those things and either prove them correct, or we'll do something else to validate them. And then OQIMP will put them all together into a circuit to create the oracle that we can then translate down to SQIR and essentially link into, say, our implementation of Grovers or Shors that we previously proved correct. Okay, so we're bringing together that missing piece of oracles off from the side into the overall quantum algorithm so we can have a highly assured final result. Okay, so the contributions of this work then are first, perhaps the most novel, is OQASM for expressing quantum oracles or elements thereof. And the key idea is to ensure that even as you use quantum behavior in the definition of your oracle, you don't introduce entanglement, assuming that you started with qubits that are just normal bits. We have a certified compilation from OQASM to SQIR. We've proved that compilation correct. And because we were able to prevent entanglement, we actually have a very, we have an O of n rather than O of 2 to the n state representation, which allows simulation to be possible of your oracles. And from that, we can do a property-based testing framework where you can just run thousands of randomized tests to assure that your oracle is correct. As a result of doing this work, we built a bunch of oracles, and we were the first to verify several. And we used property-based testing to validate many of the others seem to work correctly. And then OQIMP is also a contribution. It's not very interesting in and of itself, aside from the fact that it leverages partial evaluation in order to massively optimize the size of the generated circuits. And I'll show you what that one aspect of OQIMP looks like at the end. All of this is available on GitHub, along with all of the rest of our stuff, so that InQuire group level repository has VQO and Box and SQIR and lots of other stuff. I just wanted to point out again, Lee is on the job market. He's the one who is the lead author in this paper, but couldn't be here to present today, unfortunately. And I also wanted to point out Finn, who's fantastic. So if in maybe 2 years from now you're looking to hire somebody with PL and quantum interests, Finn is amazing. Yeah. Okay, so for the rest of the talk, I'm going to tell you a little bit about OQASM, the state structure of OQASM, why it is that we're able to do the simulation in an efficient way, the language syntax, type system, and meta theory, and then finally how we implemented property-based testing. I'll tell you a little bit about OQIMP, and then what we did with these two things, how we evaluated them. Okay, so in OQASM, in contrast to normal quantum computing, where you remember we have that single qubit that could have those two complex numbers in it, and that if you have n qubits, you have 2 to the n complex numbers. States are represented more simply in OQASM. They can be in one of 2 modes, either the normal mode or the phi mode. So in the normal mode, they represent just plain old bits. They're either going to be 0 or 1. In the phi mode, they're in superposition. So the states generally have the format that's shown up here. So basically they are, in the limit case, if that R parameter there was 0, then it's just going to be that same plus state that we saw at the very beginning. But if R, this is a rotation, a phase element, if it changes, then they're all going to have this general structure. So as I'll talk about a little bit later, this general structure is very easy to represent in a simulation. Oh, and this is just showing you how the notation that I have up there with the kets added together just boils down to the same vectors that I showed you a few slides ago. Okay, so here's the syntax of the language. The inputs to a particular operation in OQASM are positions. So they're basically a variable which can consist of multiple qubits together and an index into that thing. So you should think everything is at primitive level an array. And there's each individual qubit is identified by the array that it's in and the index within the array. So that's the xn. We have regular plain old gates that are just like the ones in regular quantum circuits. For example, the identity gate or the negation gate X. We also have meta instruction gates. So one sequence of R gates, quantum Fourier transform, and controlled unitary gate. So these are going to compile down when we compile to SQIR into multiple gates. But when you're writing your oracles, you work with them at this higher level. So for example, the CU gate is a metagate that can control an arbitrary size circuit rather than just, as is typical, a single circuit like a NOT gate. Okay, and the last line is virtual operations. So these basically shift the order of qubits inside of those variables, those arrays. So I can left shift them or right shift them, or I can reverse them. And the thing that's nice about these operations is they don't actually result in quantum operations. They're just virtual and tracked by the compiler. And again, we have this nice correctness proof in compilation, so you can be confident that, that you'll get them right. So just as an example, here's a little OQASM program. The main instruction is the CU instruction, and the first qubit there is A0, the array A and index 0, and it is controlling the circuit that's in the parentheses that follows, which is just an identity gate with A1, followed by a negation gate with also an A1. So then that's visualized over here on the right. Okay, so that's just showing you how the BNF maps to circuits. Okay, so I want to mention the quantum Fourier transform and the sequenced R gates. So quantum Fourier transform is an important part of many quantum algorithms. It's just the quantum analog to discrete Fourier transform. This is what it looks like. So this is a QFT of 4 qubits. It starts with a superposition. So you can see that in the beginning of each of these things, there's one of these H gates. And then it applies Z-axis rotation. So it's going to modify that phase component in the phi representation that we saw in the states before, rotating it by the subscript that's there. So for example, when I have that QFT NX instruction, basically it's going to expand to the circuit that's on the left inside of your final oracle. This allows you to do approximate QFT. So if you have a QFT of n qubits, but you only rotate the first m of those where m is less than n, it won't get you the complete Fourier transform. It won't properly represent all those phases in the other space. But oftentimes that's good enough, and it will save you a bunch of gates as a result. And that can be very useful in reducing your resource usage. So the point is that the algorithm, or the language allows you to use approximate QFT if you want to. SR is just a sequence of R gates. So an SRM that's shown here at the bottom is just a sequence of gates here with varying rotations. And it's going to end up yielding states that look like the one that's shown there. Okay, so now for the type system. The type system has two purposes. One is to limit the operations in each of the two modes that I mentioned so that things don't get out of whack. And you can think of that as implementing in the type system this little state machine. So for example, the rule for checking a QFT instruction makes sure that the thing that you're checking, X, the array, is in the normal mode. I'm not allowed to apply QFT to something I already applied QFT to. And so you can see here in our state machine, if I have something that starts in normal, then it's going to move it over to the left into this phi n node. On the other hand, a sequence of R gates is only allowed to be applied when you're already in this phi n mode, when you've already essentially created a superposition in some way. And so again, you can see that in the slide there that the omega x is required to be in that particular mode. For control, I'm only allowed to do controlling inside when the controlling qubits are in norm mode. The things that they are controlling don't have to be. The circuit iota there can be in superposition, but the control qubits have to be in normal mode. The other purpose of the type system is to make sure we can always track where all of the different indexes are, so that the left shift and right shift and so on are understandable for when we generate the final circuit. And so that's what this neutral prefix is doing. It's saying that, well, if you shift to the right 2, and then you better shift back by another 2 by the end of the circuit that the control is controlling, for example. So here's an example of an adder that's implemented using the QFT operation. And we can see how the type system and OQASM allows us to express that. So we start by doing a QFT, which switches the input array B's mode into phi mode. So that's all good. QFT inverse will undo the QFT and will take us back to norm mode. In the middle, we're doing these control SR gates, and this is going to be fine because the bits for array A are always going to be in normal mode, so that will satisfy the rule for the control gate, even though the other ones are in superposition. And then we're just going to basically cascade here. The way to think of it is that every bit in the top element of bits that's used as a control bit is going to affect the phase of the corresponding B bit. So essentially what's happening is when you're adding two numbers together, effectively you're changing the phase of the B gates, of the B bits, according to whether A is 0 or 1. Once I've affected those things in the phase of these bits that are in superposition, when I undo things, it's going to reflect the addition back into the basis of the gate when I'm finished. And we'll see at the end what the main benefit of using a QFT-based approach is it reduces the number of qubits that you need to add two numbers together. Otherwise, for the classical approach, you end up needing lots of ancilla qubits that take up extra resources. Okay, so the meta theory for OQASM is kind of your standard idea. If I can type check a particular OQASM program, and if I were to feed it a state that's a well-formed OQASM state, then I'm going to get some result from having interpreted that according to the OQASM semantics. Then whatever that result is going to also be a well-formed state. Okay, so if you give me a well-formed input and a well-formed program, when I evaluate that program, it's going to give me a well-formed output. Compilation correctness says that when I compile my OQASM program down to a SQIR program, so the SQIR program is a normal quantum circuit, that's the epsilon, and I then run the quantum program using the normal semantics, like the one I showed at the beginning with the Hadamard operations and so on with the vectors, then it turns out that the interpretation of that execution is going to match the interpretation of the execution of the OQASM program. Okay, and that's what that says. And these are things that we have proved in the Coq proof assistant. Okay, so while we could use all of this to do verification, property-based testing is a nice alternative. And so, hooray, we have this simpler state representation that allows us to do that. So we implemented in QuickChick, which is a property-based tester for Coq, the state representation so we can run these OQASM circuits. We can generate 10,000 random inputs and make sure that they always produce the right output. Okay, just briefly, as I mentioned, OQIMP is this high-level imperative language. We have two kinds of variables in the language, ones that are intended to be classical and ones that are intended to be actual inputs to the circuits and therefore could be quantum. And the nice trick is that we use partial evaluation on the classical inputs so that instead of treating them as constant wires, we're able to fold them into the generation of the final circuit. So, for example, to implement the sine function as an oracle, which you might do when doing a simulation, for example, you would implement it as a Taylor series expansion. So you have a bunch of multiplications and divisions and exponentiations. And so this is what our implementation of sine looks like in OQIMP. The red instructions are ones that involve quantum variables. That is, they involve the actual inputs to the final circuit, the x that's the input to sine. Whereas all of the other parameters have to do with, for example, the length of the Taylor series expansion. So that's not really an input to the result. And so even though it's an input to the definition of the Taylor series, that's just going to end up getting inlined and simplified away to great effect. It will reduce the number of gates pretty dramatically. Okay, so in the last couple of minutes, just a few things on what we've done with OQASM and OQIMP. We've implemented a whole bunch of arithmetic operators, and we have proved them correct, or we have validated them by running lots of tests on them. So on the lower part here, what that says is for 16 and 60 qubits, two different versions, that's how many seconds it took to run 10,000 property-based tests to confirm that these things were correct. Or in fact, we just actually proved them correct there at the top. You can see that compared to Quipper, which is a state-of-the-art framework that also provides a way of building oracles using a high-level language and also provides QFT and other sorts of arithmetic. In general, VQO does better in terms of the number of qubits and the number of gates that are required. This is just to say that having the power of verification allowed us to be a little bit more clever in the algorithms we put together. And so it's not that Quipper couldn't have done all the things that we did to make their implementation more efficient, but they didn't do it, and we were able to because we were confident in the result. Same thing down here. Notice that the QFT versions compared to the other versions, so the TOF, it stands for Toffoli gate, that's the other sort of standard way of doing arithmetic. You can see that the QFT versions tend to use either always use fewer qubits, sometimes dramatically so. So that's the reason you want to use them. And I already mentioned before that we found this bug in the specification of QFT addition in the original paper that proposed it. Actually found two bugs. One we found during property-based testing and one we found during verification. And this is a list that's in the paper of all the operators that we've implemented for both natural numbers and for fixed precision real numbers. On the OQIMP side, partial evaluation can work extremely well. We were able to reduce the number of gates for x times y divided by n, which comes up in that Taylor series expansion a lot, by reducing it by 95% of the gates by holding one or the other of those variables constant. So that's pretty nice. It's a lot better than just doing inlining. And overall, compared to Quipper, the sine oracle that we implemented uses 94% fewer gates than Quipper's version of sine. For fun, we implemented a oracle for Grover's search, where the oracle carries out the cha-cha-20 hash function. And so basically, we can search for hash collisions in sublinear time by using this particular oracle in Grover's. So basically, the oracle is going to compare the input against a bunch of pre-computed numbers in superposition, and then it's going to, in a smart way, iterate through that space so that you are able to have sublinear time in computing the result. And we're able to simulate this and see that the whole thing works, but we've basically proved it all correct. Okay, so I think I'm at the end. This paper has presented OQASM and OQIMP as methods for validating and verifying oracles, which are a big part of quantum algorithms, but somewhat neglected in the research literature, and I'm happy to take questions.
Right, questions?
You mentioned something about the partial QFT. Can you explain a little bit why somebody would want to do a partial QFT?
So the question was, why would you want to use approximate QFT? So that's a good question. So it turns out that sometimes operations that use the approximate version still have good enough precision as a result. So if you're doing something, if you're doing something involving real numbers, we heard before that things are often probabilistic, there's noise anyway, and you're going to end up running the program multiple times. So even though you don't have perfect precision, the reduction in the number of gates that you get actually ends up paying off after you run it multiple times. It turns out that the division modulo a number operation, when we use QFT addition as part of that operation, but we use the approximate QFT, we can save a huge number of gates without actually losing any fidelity when it's inside the division operator. So this is another benefit of having a testing framework, because you can try out these little optimizations or these modifications and quickly test that all the results are going to work the way you want. And actually, there's an experiment about that in the paper. And it's toward the end, you can see a table of what the reduction looks like.
I had a quick question about the comparison at the end. So I've never actually used it from what I understand. The Oracle transformer in Quipper is just meant to be like a one-to-one translation, and then it's meant to be optimized later on. Do you think did you try maybe applying an optimizer to both of them to see how the size compares afterwards?
Yeah, so in fact, I should have said that. I'm glad you asked that question. All of these are optimized. So basically, we did that, and then we ran both of them through Vox to put them on equal footing.
Okay, that's kind of what I was wondering, so that's good to hear. Thanks.
Sure. It is a nuanced comparison. So I would, if you are really curious, definitely look in the paper, and it describes all the circumstances of the comparison.
Okay, thanks. The reason why I ask is I actually work a bit on Quipper, and I was kind of interested in Oracle Generation 2. I haven't done anything on it yet, so I was just kind of curious how that compares. Thanks.
Any other questions? No, let's stay back.